welcome. What we're taking a look at today is even and odd functions, and specifically we're going to look at where those terms come from and what they tell us if we say a function is even or odd about that function. Now, as a very important warning that we have to discuss before we go any further, it is not the same to say that a function is even as it is to say that a function is even degree. Similarly, an odd function and an odd degree polynomial are not the same thing. They are actually only very, very loosely connected, definitely not related. An even degree polynomial needs the leading or highest term to be, well, even. So the degree of the polynomial, which is based off the degree of the highest degree term, must be even. Similarly, odd degree polynomials only really care about that first term, and that has to be odd. Even degree and odd degree, therefore, are descriptions of polynomials. You have to have a first term with a power of a variable, and so polynomials are what we're talking about when we say even degree and odd degree. That said, an even function and an odd function do not actually, it turns out, have to be polynomials. The origins of the names do come from polynomials. We'll take a look at that in just a moment, but it actually turns out that we do not need them to be polynomials at all to describe them as even or odd functions. Now, to see where they come from, I'm actually going to go ahead and jump into Desmos for a moment here. So let's take a look at a couple of graphs. So if we actually take a look at all of these polynomials, you might notice something about them. X squared, negative 3x squared plus 1, x to the 4th minus 3x squared plus 2, x to the 6th plus x to the 4th plus x squared, negative x to the 100 plus x to the 50th minus x squared. All 5 of these polynomials have a common characteristic. Every single power of x, every single exponent, is even. And yes, that actually does include a constant, because a constant can be thought of as that number times x to the 0, because x to the 0, remember, exponent of 0 means it's equal to 1, and that number times 1, well, is just that number. And yes, the number 0 is even. 2 times 0 is 0. It's a multiple of 2. So constants are also even degree terms. So it turns out that every single one of these terms here is even, and that is one of the big origins of the name even function. Every term has an even power of x. But we actually generalize this concept a little bit more, so let's see how we do so. Let's actually put these graphs up. So we have x squared, which is just our traditional parabola. We have negative 3x squared plus 1. That's going to be a downward opening parabola shifted up a little. And then we start having some 4th degree and 6th degree and even this kind of gnarly looking downward opening 100th degree polynomial. Yes, this is a polynomial function. It's just one that we're not very accustomed to, but it is a polynomial. And you'll notice that all of these graphs have some very interesting graphical characteristics in common. Namely, they're all reflections of themselves over the y-axis. So if you take the graph and then flip it, it looks exactly the same when reflected over that y-axis. And so if you were to cut this down the middle, you could actually print this graph, cut it along x equals 0, and you'd have two things that look the exact same but are mirror images of each other. Well, this is what we are actually looking for. That symmetry is what defines an even function. And so if we actually extend this to other functions, something like the cosine of x, which I realize in an Algebra 2 class you may not have seen yet, but the cosine of x, which looks like this, also fits this symmetric pattern. And so cosine is considered an even function, even though it's not a polynomial at all. So again, we're not talking about strictly polynomials, and the qualification for being an even polynomial or an even function is different from being an even degree polynomial. It requires this symmetry. What is an odd function then? Well, you might have a guess as to what it's going to be based on what we just said, and you'd be right if you said, oh, well, look at every single term, x being x to the 1, every single term here has an odd degree, an odd power of x. And so if we graph them all, we will once again see a certain amount of symmetry between them, but these aren't quite the same. They don't seem to reflect over the y-axis, and if you actually look up and down, they pretty clearly don't reflect over the x-axis either. So if there's supposed to be a symmetry, well, what is it? Well, I'm going to put in an extra curve here. I'm going to go ahead and put in y equals mx, just a very simple line that goes through Oh, you'll actually notice all these go through the origin, don't they? And so does this line. And I'm going to do something kind of interesting here. I'm going to go ahead and let Desmos go ahead and mess with the slope a little bit, change this line, kind of start bouncing it back and forth a little bit. And you'll start noticing, if you look very carefully, that there's some interesting things going on. For example, if I were to pause it right about, oh, say here, and I were to focus on, I don't know, let's focus on this blue curve, negative 2x cubed plus 4x. Take a look at where it touches the orange line. The point right here, 1.105, comma 1.723, and right here, wait, that's very familiar looking, negative 1.105 and negative 1.723. And granted, those are rounded values, but the point is the same. If I switch the x value, the y value switches too. And actually, if I let this keep moving and I do it for any other curve, like let's say the black curve, take a look at the 2 points that touch that line, and they're the exact same point, just with switched x and y values. This is a kind of symmetry that we call a point symmetry. It actually turns out that there is a point that every single one of these, any pair of points that fits this pattern, is going to have to cross through when you connect them with a line. And that point is the origin. So this is what we call an origin point symmetry. You're going to find that the distance from one of these points to its reflection point always has the origin as the midpoint between those two. So this is an origin point symmetry, and that's our giveaway that we're dealing with what's known as an odd function. And again, not every odd function has to be a polynomial at all. Sine of x, it turns out, is also going to be what we call an odd function. If I go ahead and let it swing back around for a quick second here, there we go. Just barely. So we end up with, interesting. Oh, come on. Let's move it a little bit further out so it's easier to see. We get 2 points that, again, match with having the same x and y values but with opposite signs. And so this is what makes a function an odd function. Now, switching back to our presentation, it turns out that we can very quickly and easily identify what even and odd functions are. So let's run through that really quickly. So an even function has a y-axis line symmetry. A reflection is its own reflection, I should say, over the y-axis. In general, we can represent this in function notation by saying that f of negative x, switch the sign on the x value in your function, and it gives you the same result as you had a moment ago. This is actually true because if every single power of x is even, then every single time you take a negative number, you're raising it to an even power and getting a positive number out of it for every single term. So all the negative values behave exactly the same as the positive values when you plug it into the function. So again, for a polynomial, every single term has an even power for the variable. And again, constants do count as even powers of variables. And this includes non-polynomial functions such as the absolute value of x and cosine of x. Whereas an odd function shows what we call origin point symmetry, and in general can be represented in function notation as f of negative x. So let's say we take the opposite value and we plug it into our function. Well, then we get the same thing as what we would have had a moment ago for our y value, except that y value is opposite, negative f of x. So switch the x value and you have to switch the y value. That's what this function notation says. For polynomials, this again occurs where every term of your polynomial is going to have an odd power of the variable. That's where the name comes from, and this also does include non-polynomials like sine of x and tangent of x. In case you wanted to take a look at the Desmos graphs and start tinkering with them yourselves, I've provided a link here for those, and hopefully this helps explain the difference between even and odd functions. Have a good day.